Welcome student to a lecture series on diagonalization of a matrix. I am Dr. Pradip Mondal, Assistant Professor, Department of Applied Science, Haldia Institute of Technology. So first to know when a matrix is diagonalizable. A square matrix A is said to be diagonalizable if there exists an invertible matrix P and a diagonal matrix D such that P inverse AP that equals to D. That is also write down AP equals to PD. Next, a theorem, a square matrix of order n cross n, then P inverse AP is a diagonal matrix D with diagonal entries lambda 1, lambda 2, lambda n, if and only if the columns V1, V2, Vn of P are linearly independent such that the condition AVI equals to lambda I Vi satisfied for each I. Now define eigenvalue and eigenvector. Suppose A is a square matrix of order n cross n, a vector V that equals to x1, x2, x2, xn is called an eigenvector of A with eigenvalue lambda if V is non-zero with the condition AV equals to lambda V. Then from this theorem and the definition of eigenvalue and eigenvector, we clearly see that when a square matrix is diagonalizable, that means we first calculate the eigenvalue and eigenvector of the matrix A. Now, for finding eigenvalue, first we know characteristic equation. The characteristic equation of a square matrix A of order n cross n defined by determinant of A minus lambda into identity matrix of order n cross n equals to 0. And the roots of the characteristic equation are the eigenvalues of the matrix. Now, first example. So that the matrix A is diagonalizable, where A matrix is given first row 5,4, second row 1,2. Then first we find eigenvalue of the matrix A. That means first we calculate the characteristic equation of the matrix that equals to determinant of A minus lambda into I 2 cross 2 matrix equals to 0. That means determinant of first row 5 minus lambda 4, second row 1, 2 minus lambda that equals to 0. Now if we simplify, we get 5 minus lambda into 2 minus lambda minus 4 equals to 0. That means this will be determinant expansion. Simple determinant expansion. These first multiply minus this multiply. Now again, if we simplify lambda square minus 7 lambda plus 6 equals to 0. If we factorize this, we get factorize this way. That means lambda square minus 6 lambda minus lambda plus 6 equals to 0. Now if lambda common, then lambda minus 6 minus 1 lambda minus 6 equals to 0. That means these two factor we get lambda minus 6 and lambda minus 1 equals to 0. And therefore lambda equals to 6 and 1. Therefore the eigenvalues of A are 1 and 6. Next, we calculate the eigenvectors of the matrix. The first eigenvector of A corresponding to the eigenvalue lambda equals to 1. Let x equals to x1, x2 be the eigenvector of A corresponding to eigenvalue lambda equals to 1. Therefore, for eigenvalue condition, Ax equals to lambda is that means 1 into x. Then from this part, we get A minus 1 into identity matrix into x equals to 0. Now we put a matrix 5, 4, 1, 2 minus 1 into identity matrix into x1, x2 that equals to 0, 0. Now if we simply calculation, then 5 minus 1 and 2 minus 1, these two and these two remain same 4, 1, x1, x2, 0. And again calculation 4, 4, 4, 1, 1, 0. Now from last part, we get first row 4, 4 multiply, that means 4x1 plus 4x2 equals to 0. And second row x1 plus x2 equals to 0. So these two equations are same. Now if we solve these two equations, we get simple x1 equals to minus x2. Next, we choose x2 equals to c arbitrary number. Then x1 equals to minus c. And the eigenvector of A corresponding to the eigenvalue lambda equals to 1r. We put the value x1 and x2, that means minus c and c, where c must be non-zero. Now, if we common c, this is also write down in this form minus 1 comma 1. Now, next we calculate eigenvector of A corresponding to eigenvalue lambda equals to 6. Again, we taking y equals to y1, y2 be an eigenvector of A corresponding to eigenvalue lambda equals to 6. Same calculation, that means ay equals to 6y. Now A minus 6 into identity matrix into y, that equals to 0. We put the value A and this minus 6 into identity matrix y1, y2, 0, 0. Next part, 5 minus 6 and 2 minus 6, y1, y2, 0, 0. Simple calculation, minus 1, 4, 1 minus 4, y1, y2, 0, 0. Now from this part, from first row, minus y1 plus 4y2 equals to 0. From second row, y1 minus 4y2 equals to 0. Now clearly see this, from these two equations, we simply get y1 equals to 4y2. Next, we taking y2 equals to d, be any arbitrary number, then we get y1 equals to 4d. Therefore, the eigenvector of A corresponding to eigenvalue lambda equals to 6 are 4d, comma d, where d must be non-zero. Since we know eigenvector always non-zero. Now, if we simple common d, then we get 4, comma 1. Now, we taking p and d. The p first we taking simple the eigenvectors in the column y. The eigenvector minus 1, comma 1 corresponding to eigenvalue 1. We write down first column. And second part, if we taking d equals to 1, and then the eigenvector corresponding to 6 are 4, 1. Then simply we put 4, comma 1 in the second column. And 1 and 6 we write down in the diagonal element, and other non-diagonal are 0, 1 and 6. Remember one thing, if we write down the eigenvalue 1 and 6, 1 in first column and 6 in second column, then the eigenvector corresponding to 1 must be write down in the first column of P. And the eigenvector corresponding to eigenvalue 6 must be write down in the second column. If we alternate these two parts, then also these two columns alternate. Next part, we calculate AP and PD. AP equals to simple multiply first row 5, 4, 1, 2 minus 1, 4, 1, 1. Now simple matrix multiplication 5, 4, 1, 1, that means minus 5 minus 4 plus 4. First row second column 20 plus 4. Second row first column minus 1 plus 2. Now second row second column 4 plus 2, ultimately minus 1, 24, 1, 6. Again we calculate PD. Minus 1, 4, 1, 1 and 1, 0, 0, 1, 0, 0, 6. Then minus 1, 0, first row, first column, second row, first row, second column, 0, 24. Second row, first column, 1 plus 0. Second row, second column, 0 plus 6. That means ultimately get same result. Now, from these two parts, that means AP equals to PD. Then AP equals to PD means P inverse AP equals to D. And this is our definition when a matrix is diagonalizable. Now P clearly non-singular and D also diagonal matrix. Therefore, we say that a matrix is diagonalizable. Now second example, we again taking a 3 cross 3 matrix. A matrix, this matrix A, first row 2, 0, 0, second row 1, 2, 1, and third row minus 1, 0, 1. First we find eigenvalue of the matrix A, that means the characteristic equation. The characteristic we write down in this form, determinant of A minus lambda into I3, 3. That means determinant 2 minus lambda, 2, 0, 0, 1, 2 minus lambda, 1, minus 1, 0, 1 minus lambda. That means diagonal element wise minus lambda. That equals to 0. Now determinant expansion 2 minus lambda, product of these two part minus this, the 2 minus lambda, 1 minus lambda minus 0. And for these two, 0, that means these two are 0. Now 2 minus lambda square, these two, and 1 minus lambda, that equals to 0. Now from this part, lambda equals to 1, 2, 2. Therefore, the eigenvalue are 1, 2, 2. So here 1 times and eigenvalue 2 are 2 times. Next part, we calculate eigenvector corresponding to eigenvalue lambda equals to 1. The x equals to x1, x2, x3 be an eigenvector of A corresponding to eigenvalue lambda equals to 1. Now same condition, Ax equals to 1 into x. Now from this part we get A minus 1 into I3 cross 3, x equals to 0. Now put the value A and n, this minus 1 into identity matrix of order 3, x1, x2, x3, 0, 0, 0. Now simple calculation 2 minus 1, 0, 0, 1, 2 minus 1, 1, minus 1, 0, and 1 minus 1. x1, x2, x3, that means 0, 0. Now if we simply calculation, we get 1, 0, 0, 1, 1, 1, minus 1, 0, 0, x1, x2, x3, 0, 0. Now from this part, first row, if we multiply, we get x1 equals to 0. If we second row, x1 plus x2 plus x3 equals to 0. And for third row, minus 1, that is minus x1 equals to 0. Now from this part, we clearly say x1 equals to 0 and x2 equals to minus x3. Now we're taking x3 be any arbitrary number. That means x3 equals to c, be any arbitrary number. Then we clearly get x2 equals to minus c. Therefore, the eigenvector of A corresponding to the eigenvalue lambda equals to 1 are 0, minus c, c, where c must be non-zero. This is also write down in this form c 0, minus 1, 1. Now, second step, we calculate eigenvector of A corresponding to eigenvalue lambda equals to 2. So let y equals to y1, y2, y3 be an eigenvector of A corresponding to eigenvalue lambda equals to 2. So therefore, same ay that equals to 2 into y. Now same a minus 2 into I, because 3y equals to 0. Put the value a and 2 into identity matrix. Now calculation, the 2 minus 2, 0, 0, 2 minus 2, again minus 1, 0, and 1 minus 2. y1, y2, y3 that equals to 0, 0. Now if we simply calculation, we get this part. Now again, first row all element are 0, that means no equation. Second row y1 plus 0 into y2 plus 1 into y3, that means y1 plus y3 equals to 0. And last row minus y1 minus y3 that equals to 0. Now if you solve this equation, we get y1 equals to minus y3. So in this equation there are no y2 part. Then we taking y2 be any arbitrary number. Since there is no y2 in this equation, that means we taking y2 equals to d, and we also taking y1, 1 of y1 and y3 arbitrary. That means we taking y3 equals to arbitrary e. Then we get y1 equals to minus e. Therefore, the eigenvector of A corresponding to the eigenvalue lambda equals to 2 are minus E, D, and E. In this condition, D square plus E square must be non-zero. That means maybe D 0, then E must be non-zero. If E 0, then D must be non-zero or both non-zero. This is the condition. If both 0, then the eigenvector is 0. But if at least one D 0 and E non-zero, that means this is also the eigenvector is non-zero. That's why you're taking D square plus E square non-zero. If you're taking D common, that is we get 0, 1, 1 and plus E into minus 1, 0, 1. And this is the condition. Now, again we write down P and D. P first D means first row, first eigenvalue 1 in the first diagonal. That means corresponding eigenvector are 0, minus 1, 1. That means we put simple c equals to 1. We get this value. 0, minus 1, 1. Second part, the eigenvector 2 in the second column and third column. So therefore, the corresponding two eigenvector, these two part, we write down in these two column. First column and second column. These two eigenvector, that means these two, 0, 1, 0 and minus 1, 0, 1 are clearly linearly independent. If we show that these two vectors, then these two vectors are linearly independent. That's why this P always non-singular. Non-singular. That means these three eigenvectors are linearly independent. That means P is non-singular. Next, we calculate AP and PD. The A equals to 2, the matrix, and P equals to, write down. Then the product AP, that means first column, we get 0. First row, second column, we get 0. First row, third column, we get minus 2. Second row, first column, we get this element. Second row, this column, we get 2. And in this process, just simple multiplication, we get this matrix. Again, similarly, if we multiply PD, matrix multiplication, 0, 0, minus 1, that means first row, first column, we get 0. First row, second column, 0. First row, third column, that means 0, 0, minus 2. Second row, first column, minus 1. Second row, second column, 2. Second row, third column, 0. Third row, first column, 1. Third row, second column, 0. Third row, third column, that equals to 2. So therefore, AP equals to PD. That means P inverse AP equals to D. So P inverse AP equals to D. That means this is the condition. The matrix A is diagonalizable. Therefore, the matrix A is diagonalizable. Next class, we discuss when a matrix A is not diagonalizable. Sometimes matrix is not diagonalizable possible. The next class we discuss this part. When a matrix is not diagonalizable.